All right, here's the lesson video 16-2. We're going to look at standing waves, but we're going to look at a particular type. It's standing sound waves. And sound waves are longitudinal waves. Up to now, we've been studying transverse waves, and now we're going to look at a standing longitudinal wave. So here's some examples of standing sound waves. Here's a dog howling, and the dog's throat acts like a tube, and it's a closed open-end tube, and so you'll see a couple of different wavelengths here. So the dog can actually resonate at a couple of different frequencies. We'll also see standing waves occur in musical instruments as well. So we want to look at the three different types of tubes we'll investigate when studying standing sound waves. The first one being an open-end tube. That means it's open at both ends, and the tube's empty in the middle. Is just air inside there. And the sound wave that we have the inside of this tube at m equals 1, the first harmonic, is very similar, looks very similar to the first harmonic for the string fixed at both ends. As a matter of fact, the equations are exactly the same for both. And then as you can imagine, when we go to m equals 2, it looks very similar to the strings as well. Open at both ends, m equals 2. So we have something that looks like this. And then actually, in this case here, I should have wrote down that the length of the tube equals half a wavelength for m equals. And then for the m equals 2, the length of the tube equals 1 wavelength. Now let's look at m equals 3. And in this case here, the length of the tube is 3/2 of a wavelength, or 1.5. The next type of tube is a closed. So actually, let me just write this that we did here. This was open. And the next type of tube we're going to do is called closed. So here I have 3 tubes that we're going to use as closed, and I shaded in the ends to show that it is closed. And we're going to look at the first harmonic, the second harmonic, and the third harmonic. And what's interesting about this is they'll use the exact same equations that we had for open tubes and the same equation for fixed. The waves, though, look a little bit different. So in this situation, we have the waves looking like this, but it's still, the length of the tube still is half a wavelength. And then when we go to the next tube, m equals 2, we have this situation where the length of the tube is a full wavelength. So it's the exact same pattern, it's just slightly different looking wave inside of there. I mean, we have half a circle on the first one and half a circle, so that's a full circle. And on this one, we have 2 full circles. And so m equals 3, we'll have 3 full circles. So our m equals 3 has a wave that looks like this, and the length of the tube is 3/2 of a wavelength, or 1.5. The mathematics is the same for all the different types of waves we've talked about so far. The last type of tube, though, is the one that's different. It's the open-closed tube. That's the one we did in lab yesterday. So we have these 3 tubes here, closed at one end, right here, and open at the other, shaded in regions of the closed end. And so now we're going to fit just a 1/4 wavelength inside of these tubes. So here I've drawn a 1/4 wave inside this tube. So the length of this tube is a 1/4 wavelength. Now we'll go ahead and draw the next tube will be 3/4 of a wavelength. So here's what the wave looks like inside this tube. The length of the tube is equal to 3/4 of a wave. And then the last one is going to be 5/4 of a wave. And so we have, again, I had to cheat a little bit in my drawing. Well, it's 5/4 of a wave. And then it would be 7/4 and so on. So this is the third type of tube we're going to look at. And its equation actually, the equations for this one actually are different than for the other 3. And as you can see, Number 3 says draw the standing wave for each tube type. Well, I've done that up above there in number 2, but you can draw those in the number 3 spot. And so for the fourth section here, we're going to look at the equations. What are the equations for calculating the wavelengths and frequencies for the different tubes? Well, if you look at open or closed tubes, as well as strings fixed at both ends, you'll use the above equations. So if you'll notice this looks familiar, hopefully. Wavelength equals 2L over M. We did that for strings fixed at both ends. We did frequency equals M times V over 2L. That works for these types of tubes also. And also, here's a new one that we learned about in the lab, M times F1. So if you want to go to the next harmonic, you can take, if you want to go to the third harmonic, you just multiply your first frequency by 3. If you want to go to the second harmonic, you multiply your first frequency by 2. And you'll see M equals 1, 2, 3, 4. So if you want to go up by harmonics, it's 1 times F1 is your first frequency, 2 times F1 is your second harmonic, 3 times F1 is your frequency for your third harmonic. So these are different equations for strings fixed at both ends, open tubes, or closed open tubes. Now we can take a look at the equations for the last type of tube, the open-closed tube. Here, you notice the equations are a little bit different. Let me just kind of scroll up here so we can compare. Instead of wavelength being 2L over M, its wavelength equals 4L over M. And that's because the first harmonic has a quarter wavelength instead of the half wavelength. Remember, this is for open, closed tubes. The frequency equals M times V over 4L, not V over 2L. That's for finding the frequency of the different harmonics. But this is the same for both of them. As you want to go from one harmonic to the next, all you do is multiply the frequency but by 1, but then it goes 1, 3, 5, 7. The M isn't 1, 2, 3, 4, 5. You have to remember, the M is all the odd numbers. So you don't use 2, 4, and 6. So when you go from one harmonic to the next, you have to use 1, 3, 5, 7. So it's a little bit tricky in the sense that this is the first harmonic, 1 is the first harmonic, 3 is the second harmonic, 5 is the third harmonic, 7 is the fourth harmonic. So you have to pay attention to that you go 1, 3, 5, 7 to go from first, second, third, fourth harmonic. So I'm going to do an example problem here with you. This is on page 512 in your textbook. We're looking at the resonances of the ear canal. The eardrum, which transmits vibrations to the sensory organs of your ear, lies at the end of the ear canal. The ear canal in adults is about 2.5 centimeters long. What frequency of standing waves can occur within the ear canal, that is, within the range of human hearing? The speed of sound in the warm air of the ear canal is 350 meters per second. And humans can hear between 20 hertz and 20,000 hertz. So we have to find out what frequencies will resonate inside of our ear canal. So we have to realize that this is a tube that's open at one end and closed at the other. So we're going to look at this as if it's an open, closed tube. And so my frequency equation is frequency equals M times V over 4L. So we'll go ahead and plug in our values here. Our frequency for the first harmonic is M is 1 times the velocity is 350 meters per second. Over, since we're using meters, we better change our length to meters. So instead of 2.5 centimeters, it's 0.025 meters. And so that frequency is equal to 3,500 hertz. What that means is 3,500, if we listen to 3,500 hertz, it will resonate inside of our ear canal, and actually that 3,500 hertz frequency will seem very loud, louder than it normally would. A 3,000 hertz sound would just sound like a regular sound. But 3,500 hertz would actually resonate and become a larger sound inside of our ear. That can be a painful sound for us. Let's find out what other frequencies this occurs at. So we're going to do a harmonic of the second harmonic. And remember, if we do the second harmonic, M equals 3, because this is a closed open tube. My harmonics go M equals 1, M equals 3, M equals 5, and so on. So the second harmonic, M equals 3. So you have to remember that. You have to pay attention to that. It's 350 meters per second all over 4 times the 0.025 meters. And that frequency ends up equaling, it has a value of 10,500 hertz. So again, if we hear 10,500 hertz frequency, which we don't very often, it's a very high pitch, it will resonate and become very loud. The third one is 5 times 350 meters per second, all over 4 times 0.025 meters. And that comes out to be 17,500 hertz. And again, if we listen to 17,500 hertz, it'll resonate inside of our ear canal, and it'll sound very loud. It might even be a painful noise. Our ear canal is very short, and so it makes sense that the higher frequencies are the ones that are going to resonate. The higher frequencies have shorter wavelengths, therefore they'll resonate inside of our ear canal. And that's the conclusion of this video.